So we left off talking about how exothermic reactions mean energy is released and endothermic reactions mean energy is absorbed. And why does all this happen? So in your molecules, there's bonds. And a bond is energy that's holding the atoms together. And so there's energy in the bond. And depending the properties of the elements that you're working with, it can be a strong bond that has a lot of energy that you need a lot of energy to break, or it can be a weak bond that's really easy to break. And if you think about it, if you want to break something, you need energy to do it. And so breaking bonds in general is an endothermic reaction. You need energy to break the bonds. So that means that when you make bonds, it's got to be exothermic. And why is that? And so in the exothermic reaction, when things make bonds, they're going from a high energy state to a low energy state. So making bonds creates more stable molecules. Low energy is more stable. They wouldn't make the bond if it meant they had to have more energy. Do you want to do things that means you have to use more energy? No, same idea. And so you're going from something that has high energy, it made a bond to get to low energy, and that high energy had to go somewhere, and so that energy goes out, like an exothermic reaction. So when we make bonds, that's exothermic, because you go from a high energy to a stable low energy state. And so bond energy, the number that we're going to say is bond energy, is the amount of energy required to break a bond, because that's what we can measure. We can throw a bunch of energy into a system and determine if the bonds are broken or not. And so we know we need 413 kilojoules per mole. That'll be important later, not right now, but later, to break a carbon-hydrogen bond. We need 495 kilojoules per mole to break oxygen gas bonds. And so if we want to come up with that number ahead of time, let's say you're working for an industry and you want to know how much energy you theoretically need or is released, you're going to take the sum, this funny looking thing right here means sum of the reactants, all of these bond energies, and the sum of all of the bond energies in the product side, and then subtract the two. So step one, we're going to identify all the bonds that we have. So we have CH bonds, we have oxygen bonds. And so if we remember, oxygen has a valence of 6. It wants to share 8, or it wants 8 in its valence, so it needs to share 2 to have a total of 8. 6 plus 2 is 8. So we need 2 bonds, these 2 lines, these double bonds, to make the 2 oxygen molecules stable. This coefficient right here, the big 2, says that we need 2 molecules. So little 2 tells us how many atoms. You gotta use your brain to think about how many bonds. Coefficient, the big number, tells us how many molecules. On the other side, we have carbon and oxygen double bonded, and water looks like this. H2O is water. We have hydrogen and oxygen bonds, so an OH bond. Step 2, we're going to count up all those bonds, and then we're going to multiply by the bond energy from that table that we saw earlier. So if we look at CH, we have 1, 2, 3, 4. So 4. We have 2 double bonds. Even though there's 4 lines, there's 2 bonds. So we use 2 to describe the number of bonds, not the number of lines. On this side, we have 2 bonds in the carbon dioxide, and we have 1, 2, 3, 4 bonds in the water. So the 4 there. These numbers in the parentheses came from that bond energy table. Carbon and hydrogen, 413. Oxygen and hydrogen, 467. And so that's where these numbers came from. And you'll always be given the bond energies in most situations. You shouldn't be expected to know them. Just what to do with them. So you multiply across, add them up. Same thing on this side. We multiply these numbers, add them up. And then we subtract both sides and we get negative 824 kilojoules per mole. So that number is negative, and if you remember, negative enthalpy means energy was released, which is exothermic. So this is an exothermic reaction. You release energy to do it. Let's try another one. So we have ethanol breaking down into ethene and water. We have our CH bond, our OH bond, C double H, C double C, OH over here, and I have the two that weren't, on the other slide previously. We have 1, 2, 3, 4, 5 CH bonds, 1, 2, 3, 1, 1, and 1 of the other bonds. On this side we have 1, 2, 3, 4 CH bonds, 1 carbon double bond, and 2 of the OH. Again, I got these numbers from our table. Carbon-carbon, 348, carbon double bond, 614. And then again, we add them up and subtract. This time we get a positive number. It's 38 kilojoules per mole. So that means that positive enthalpy means positive energy. You need energy to make that reaction happen. It's endothermic. And if we look, we took this molecule, we broke it off here, and we stuck that H on over there. So we broke bonds, we broke more bonds, and we made bonds. So we need energy to break those bonds. So it's endothermic. That makes sense. So you try the next one, pause the video, count up all your bonds, find the bond energies, add and then subtract, and then I'll see if your work matches my work. So I got negative 168 kilojoules per mole. I have my bond energies, my number of bonds. Subtract the 2, I got negative 168 kilojoules per mole. So that'd be an exothermic reaction. Here's another one for you to try. Notice there's a 2 here. That means there's 2 molecules of NH3. And so I have 2 times the 3 bonds right there in my work. And I got 91 kilojoules per mole. 91. And so since that's positive, that's endothermic. Endothermic. And that's it. That's the end. The next video will be reaction coordinate diagrams.